So in today's topic, we will be looking into thermal equilibrium and what is meant by MCP delta T, what are the modes of heat transfer available, what is meant by heating and cooling, temperature time curve, what is the significance of having a low specific heat capacity substance and high specific heat capacity substance, and we will look into some problems as well. So to start with, what is meant by thermal equilibrium? So we all know, let's split this into two parts, thermal and then equilibrium. Equilibrium means, say for example, you are taking a body. Let's say this is like a block of wood. So this is resting on top of a table. So let's assume this is a block of wood that is resting on top of a table. So it's not doing anything. So it is not doing anything mechanically, it's not doing anything thermally. So which means if it is not doing anything, then it is said to be in equilibrium. And if it is not doing anything with respect to temperature, that means it is thermal equilibrium. So here the wood is not giving any heat to this table. This table is not giving any heat to this wood. Neither the wood or the table is not giving any heat or receiving any heat from the surroundings, which means there is no heat interaction happening within all the objects present in here, wood, table, surroundings. So that means they are in thermal equilibrium. Let me give one simple example. Let's assume you are going in a car. Okay, so assume that this is a car. So you are going in this car and the outside temperature is 25 degrees Celsius. So now you are somehow you are feeling uncomfortable and you are trying to switch on your AC and you are switching that AC to 25 degrees Celsius. So now what will happen is the temperature outside of your car is 25 degrees Celsius and you switched on your AC and switched on to the mode of 25 degrees Celsius in the car's AC. So now if you look at the temperature difference, right, there is no temperature difference at all between outside of the car and inside of the car, which means though you switched on the AC, there is no heat transfer happening from surroundings to AC, the car, and from car to this surroundings, which means both the car and the surrounding is in thermal equilibrium. There is no heat transfer happening between this car and the surroundings. So now let's take the same temperature outside is 25 degrees Celsius. And you reduce the temperature in your car from 25 degrees Celsius to 15 degrees Celsius. So now obviously, like in the previous discussion, what we did is like whether the body is hot or cold, how we determined. We compared it with against the outside temperature. Outside temperature is 25 degrees Celsius, which is higher. And the car's temperature is 15 degrees Celsius, which is lower compared to the outside temperature, which means car is cold body now. This is cooler compared to the surroundings. And now there is a temperature gradient. Gradient means there is a difference between the temperature of the car and the temperature of the surroundings. So the car and the surrounding is not in thermal equilibrium because their temperature is not equal. So now you can get an essence of what thermal equilibrium is. Thermal equilibrium is nothing but the body that you are comparing. For example, if you are comparing a block of ice against any surroundings, the surrounding is also at the same temperature as the ice, 0 degrees Celsius surroundings, and the ice, we all know that it's at 0 degrees Celsius. So if both are at same temperature, that means it's in thermal equilibrium. There won't be any interaction between the ice and the surrounding to ice. So you should ask me one question, why we are learning about this thermal equilibrium? Because all our problems we will solve based on this thermal equilibrium only. So we will assume that the final state of the bodies that you consider for your problems will be in thermal equilibrium. So then only you will attempt for the problem solution. Now that we have seen about thermal equilibrium, which is an important topic to solve problems, the second most important thing is like what is meant by MCP delta T and how it is related to heat transfer. So this is the second point that we are going to discuss. But if you come to the fifth point, the temperature time curve, we can just closely relate this MCP delta T and temperature time curve. While understanding, it is better to understand these 2 points together, for which we will go for an example. I will just divide the board into 2 separate segments. First one is I will go for a physical example. And the same physical example will be manifested in a way that you will understand it graphically. So what is meant by physical example? Physical example is nothing but I'm just going to depict what you are going to see in real life. So first, let's take a plate of ice. This is ice at minus 50 degrees Celsius. So we all know that in general ice is going to be at 0 degrees Celsius, but that is a normal ice, but this is a super cooled ice. So super cooled ice can be like in any temperature which is below 0 degrees Celsius. So now this is minus 50 degrees Celsius. So the same way, I will just use two different colors. For graphical, I will use blue color. And for the example, I will just, this is time. This is temperature. This minus 50, so I will just have a scale as well. Like let's assume this is minus 50 degrees Celsius. This is 0 degrees Celsius. 50 degrees Celsius, 100, 150. This is 1 hour, 2 hour, 3 hour, 4 hour, 5 hour. Okay, so this is the scale that we have for the graphical representation. In many of the books, this time will be given in seconds, but that is okay. You can take it in any time. Even 1 hour, you can take this as 3600 seconds. So now coming back to the physical representation, now you have a plate of ice which is at minus 50 degrees Celsius. You are letting it as it is for 1 hour. Okay. So now what happens is this ice will change into similar ice, but you just want to note down one critical point here. This is ice at 0 degrees Celsius. This is state 2. Same plate, but this is not minus 50 degrees Celsius ice. This is 0 degrees Celsius ice. This is at the end of 1 hour. I can say this is at 0th hour. This is at 1st hour. Okay, so now how can I depict this in this diagram? This is very important. This will be asked in your public examination as well. So now the first state, ice minus 50 degrees Celsius ice. So let's assume this is here, stage 1, because this is the 0th hour and your ice is at minus 50 degrees Celsius. Fine. Now when you are taking the second stage is after 1 hour. Your ice is at 0 degrees Celsius, which means if you plot, it will be coming somewhere near here. So this is your state 2 and you can connect this like this. Okay. So this is a linear graph, linear line joining point 1 and 2. So this will represent the temperature time curve of ice, which is transitioning from minus 50 degrees Celsius to 0 degrees Celsius. And what is happening in this 1 to 2 stage will come at the end of this temperature time curve discussion. So now, after this, what will happen if you let it for another 1 hour? Keep for another 1 hour. So which means it is at 2nd hour. So at the end, what will happen is this ice will melt into water. So you will have a plate. The plate will have water at 0 degrees Celsius. Okay, so this is stage 3. And the key point you will be here, it might be like very simple for you, but if you go to the diagram in graphical representation, you will note the key difference, what is happening here. I am just extrapolating this point. And now if you see, this is ice at 0 degrees Celsius, this is water at 0 degrees Celsius. So there is no change in temperature. So temperature is going to be same. So this is your point 3. At the 2nd hour, the water is at 0 degrees Celsius. So the line will be like this, horizontal. What is happening between this 2 and 3? The line is horizontal. What is happening there? We'll see that as well at the later point in time after completing this graph. So now coming back to the physical representation. Now at the 4th hour, what is happening? Now again you are leaving it for another 1 hour. So this is the 4th hour. Sorry, my bad. This is the 3rd hour. Because 0, 1, 2, it's the 3rd hour. So now what will happen is water will start to heat up. So what will happen to water? Water will slowly attain room temperature. Assuming that room temperature is 25 degrees Celsius, or okay, let's assume the room is 25 degrees Celsius. Keep it this way. So now if you go to that diagram again, so the end of third hour, if you just extrapolate this point, and this is some, the 25 degrees Celsius will be somewhere here. So this is my fourth point. So this will be something like this. So here, first to second is a linear curve, but it's an inclined curve. 2 to 3 is a straight curve, straight line, but it's a horizontal line, simple flat horizontal line. But 3 to 4 again, it's an inclined line. So there is some significance happening in this curve as well. So we will discuss that now. Before that, you will have one question. So, like you know that ice is at minus 50 degrees Celsius, there is some temperature change going on, there is some phase change going on, again there is a temperature change going on. So somebody has to supply the heat to ice, or somebody might be taking in taking away the heat from ice. So something should be happening, that is the heat transfer actually. So now what is happening is, when you are exposing this ice to atmosphere, assuming the atmosphere is 25 degrees Celsius, and why I am mentioning this 25 degrees Celsius and here 25 degrees Celsius, I will come to that now. So now the first stage, you are just exposing this ice at minus 50 degrees Celsius for 1 hour. So what is happening is, this atmosphere is giving in heat. Let me draw it in red color. So the atmosphere is giving its heat to ice. So now ice is gaining heat, it becomes 0 degrees Celsius. So how you can say something is gaining heat? There are two ways. One is, it is changing its phase from solid to liquid. That is one thing. The second thing is, it is increasing its temperature. So minus 50 degrees Celsius to 0 degrees Celsius. Yes, it is increasing in temperature. So it's a heating process. So somebody should be supplying heat to the ice, which is nothing but the atmosphere at 25 degrees Celsius. Again, if you come to ice at 0 degrees Celsius, again, here comes the first point that I was telling you what is meant by heating. So this is ice at 0 degrees Celsius, this is water at 0 degrees Celsius. There is no temperature difference, which means you may think that there is no heating happening. But if you see the phase, this is ice, which is a solid, and this is water, which is a liquid. So there is a phase change happening. So that means when a phase is changing from solid to liquid, ideally there is a heating process happening. So who is supplying the heat? Again, the same atmosphere at 25 degrees Celsius is giving heat to ice at 0 degrees Celsius to make it water at 0 degrees Celsius. Now again, you are leaving it for another 1 hour. Now the water at 0 degrees Celsius again is taking heat from atmosphere at 25 degrees Celsius, and it is becoming water at 25 degrees Celsius. Why this is attaining 25 degrees Celsius is the good question, which we are coming back to the thermal equilibrium point again. So at any point in time, the maximum temperature the water at 0 degrees Celsius can attain by heating process is the maximum temperature of the atmosphere, which is nothing but 25 degrees Celsius. So let's assume that water is becoming 26 degrees Celsius, which is hypothetical scenario. It can never happen, because heat will always flow from higher temperature to lower temperature. That is why from 25 degrees Celsius, heat is flowing to water at 0 degrees Celsius to make it water at 25 degrees Celsius. I think so it's a bit of confusing. I will just give a recap once the diagram is done. So here, there is one more part here. So right now we are stopping at water at 25 degrees Celsius as per ICSE syllabus. But there is one more category which is possible with this temperature time curve. So just a step, we just want to go out of ICSE and learn a bit more. For that, what I will do is, the same diagram, let's assume the same diagram, but the only change is, this is not an atmosphere. Rather, I am taking this as a surrounding at 150 degrees Celsius. Earlier it was atmosphere at 25 degrees Celsius, now it is changing to surrounding something. You can take that as a heat exchanger, you can take that surrounding itself, atmosphere itself as a 150 degrees Celsius. It's just a hypothetical situation. So now this process remains same, but this process will have some difference, because Earlier, the maximum temperature this water can reach is the temperature of the surrounding. But now, the temperature of the surrounding has changed to 150 degrees Celsius. So, it can reach up to 150 degrees Celsius. But water has a limitations at 100 degrees Celsius. After 100 degrees Celsius, it starts to become steam. So, what will happen in that case is, during the transition of the third hour, this point, water at 0 degrees Celsius to water at 25 degrees Celsius, this will change to boiling water, which is nothing but water at 100 degrees Celsius. I am just changing the diagram a little bit. So now that this is my third point, second hour, and I am just extrapolating this 100 and this third. Ideally to the scale, this is not correct. Let me recorrect the scale. Third hour, fourth hour. So now let me extrapolate this third hour. 100 degrees Celsius, the water is becoming 100 degrees Celsius now. Why it's not 150 degrees Celsius? Because water has a limitation that after 100 degrees Celsius, it will start changing phase. Means water will get converted to steam. So the maximum temperature water can attain is 100 degrees Celsius at atmospheric pressure. If you are increasing the pressure, water can go beyond 100 degrees Celsius. But we are talking about atmospheric pressure, that is normal surroundings, how we are living in. So in that case, water will be available only at 100 degrees Celsius. Beyond that, it's not possible. So now we are having water at 100 degrees Celsius here. So this is also an inclined curve. Why this is inclined, why this is flat, we will come to that. Now again, still we have like 150 to go. We can go till 150. So what will happen now is, subsequently, as I said, the water has a limitation of 100 degrees Celsius. After that, it will change phase. Now I am leaving fourth hour. I am giving one more hour for the water to boil. So what will happen is, water will convert to steam. So now water will become steam at 100 degrees Celsius. Okay, so now it was ice to 0 degree ice, then again water at 0 degree, water at 100 degree. Now again you are giving, this is first hour, second hour, third hour, this is fourth hour. So if you are leaving for fourth hour, water is getting converted to steam at 100 degrees Celsius. You can look at the same case as here, 0 degree ice to water at 0 degree. Here also same as water at 100 degrees Celsius and steam at 100 degrees Celsius. Going back to the graphical representation, I'm just extrapolating the fourth hour. So this is my 0.4, this is my 0.5. So now here you can see that water at 100 degrees Celsius, this is that point. This is changing to steam at 100 degrees Celsius. So here the curve is again a flat horizontal curve, not an inclined curve. Why this is not an inclined curve, we will come to that. Now still we have some scope because this is at 150 degrees Celsius. You can still make it 150 degrees Celsius. Now you are giving one more 1 hour, fifth hour. So now what will happen is, your steam will become 150 degrees Celsius. So the same thing I am just extrapolating here, the fifth hour. And I am just repeating, this is a key questions you will definitely be asked in ICSE examination. You can expect this as like a 3-mark question or a 2-mark question in any of the public examination paper. And I am just extrapolating this as well. So I should not extrapolate 100 degrees Celsius, rather I should do 150 degrees Celsius because that is the maximum temperature time. This is the sixth state. So now if you can go and see this diagram, 150 degrees Celsius, 150 degrees Celsius, we have attained the maximum. So is there any possibility for the steam to attain more than 150 degrees Celsius? Not possible, because the surroundings, the person who is giving you heat itself is at 150 degrees Celsius, and you have attained that maximum 150 degrees Celsius, which means surrounding and the steam, the system, both are in thermal equilibrium. You are at 150 degrees Celsius and whoever is giving you that heat is also at 150 degrees Celsius. Both are in thermal equilibrium. So if the body is in thermal equilibrium, there will be no heat transfer. So you can just think of this diagram. You can just make a note of this diagram. Now I will come back to this again. Now we will go to the graphical representation and see what is happening. So now let me take minus 50 degrees Celsius ice. So the ice is at minus 50 degrees Celsius. So what is happening is surrounding at 150 degrees Celsius is giving ice at minus 50 degrees Celsius some heat in the form of heating in the heating process, and this can be analyzed by using the temperature gradient, 150 degrees Celsius minus 50 degrees Celsius. So whenever you are having a heat transfer process by virtue of some change in temperature, right, that is like normal MC delta T. This is the normal heating. Okay, or technically what we call this as conduction. Okay, so this is normal conductive heat transfer. Second, this is like most of the cases we will see this inclined curve, but 2 to 3, this to this, if you see, this is ice at 0 degrees Celsius becoming a water at 0 degrees Celsius. So this is, you cannot see any change in temperature. This is 0 degrees Celsius, this one is also 0 degrees Celsius. If you do MC delta T, you will see 0. But this one surrounding is giving enormous amount of heat energy between this 2 and 3 process to make it water at 0 degrees Celsius from ice at 0 degrees Celsius. So this is called latent heat. We all know that latent means it is hidden. Why this is hidden? Because you cannot essence it by seeing the temperature difference. There is no temperature difference. There is only phase difference, and that too, comparing this heat will be like in hundreds and thousands of times more. So phase change will always be having a huge amount of heat transfer. That's why you can see this as a flat line. So you will not see any temperature difference. Okay, now moving to the 3 to 4 curve. So what is this 3 to 4 curve saying? That is this to this. So water at 0 degrees Celsius gaining heat from the surrounding, which is at 150 degrees Celsius, and becoming water at 100 degrees Celsius. Again the same case. This is a very simple case of conduction heating. So from 3 to 4, it's simply taking in heat, skyrocketing its temperature to 100 degrees Celsius. Fine, it is hitting the water maxima. Water can attain only a maximum of 100 degrees Celsius before phase change. So once it attains 100 degrees Celsius, again it's taking heat from the surrounding, which is at 150 degrees Celsius, and converting it into steam. So here also you can analyze this as the same way as the ice at 0 degrees Celsius to water at 0 degrees Celsius. The same steam at water at 100 degrees Celsius is becoming steam at 100 degrees Celsius. There is a phase change happening. So this is also called latent heat. The difference between these two latent heat is, this is changing from solid to liquid, so this is called latent heat of fusion. And this is from water to a gaseous state, so this is called latent heat of vaporization. Okay. And after that, there is one more, like water from 100 degrees Celsius to steam at 100 degrees Celsius, and the last one is, the steam can also be superheated. This is called superheated steam. The steam after 100 degrees Celsius, like 101, 102, 103, those are called superheated steam. In our case, it is taking in a lot of heat at 150 degrees Celsius and it attaining 6th state. So this is how the diagram goes. And most important questions that will be coming into picture for you in ICSE is, and from the syllabus perspective, you can just cut down here itself. You will not have after 3rd hour. The hours that I am mentioning is just for understanding perspective. It's not like exact hours. You can mention it as T1, T2, T3, T4, T5. It's not exact 1 hour, 2 hour. So we will not have this portion of steam and all in our ICSE. If you want, you can read that as well. You can request me. So currently our scope is only this. So I will just redraw this diagram to understand the potential questions and how to solve problems. Same curve. I am just reiterating because it's a very important question. So I'm just repeating it again and again. So let's assume minus something, minus 50 degrees Celsius, 0, 50, 100, 150. This is temperature increasing in this direction. This is time, in this direction. But here, to confuse you, I will just put this as T1, T2, T3, T4 and T5. Okay. So now what will happen is, why I am rubbing this has some reason. I will just tell you that. Assume this is T1. So this is your first state where you had ice at minus 50 degrees Celsius. Now you are going to ice at 0 degrees Celsius. Then again, you know that it's going to be a flat line till this point. And you are going to get, so now this is ice at 0 degrees Celsius, water at 0 degrees Celsius. So now again T3, water is going to heat up at 100 degrees Celsius. This is water at 100 degrees Celsius. And then let me not leave this elsewhere. Let me just give you some sort of knowledge on this. So now what will happen is, again water will get converted to steam at 100 degrees Celsius, and the 100 degrees steam will again skyrocket to 150 degrees steam. Okay, so you can ignore this part for now. This is passport. So I am just marking some dotted lines in red. You can ignore whatever is there in the right for ICSE. Okay, so take this part. You can see the inclination of this ice at minus 50 degrees Celsius to 0 degrees Celsius ice compared to water at 0 degrees Celsius to become water at 100 degrees Celsius. What can you infer? This is an important question, ICSE question, that is asked in 2018. So if you see the inclination of the ice changing from minus 50 degrees Celsius to ice at 0 degrees Celsius will be more compared to the inclination of water at 0 degrees Celsius to become water at 100 degrees Celsius. This is because, this is very, very, very important, because ice is having a specific heat capacity of closely to closely 2 kilojoule per kilogram Kelvin. This is for ice. Okay, the same specific heat capacity, if you check for water, it will be approximately 4 kilojoules per kilogram Kelvin. So what does this mean? This means ice will take only less heat to rise its temperature, but water will take in more heat to rise its temperature. So as we move on to the temperature, like for example, move on through the time. For example, take minus 50 degrees Celsius and leave for 1 hour. Let's assume it is taking X kilojoules of heat to rise through 0 Kelvin. If you give the same amount of heat to the water at 0 degrees Celsius, it will be close to only half the temperature of what this ice has reached. Which means ice at minus 50 degrees Celsius will reach a temperature of higher ice. For example, minus 50 degrees Celsius ice can easily go to minus 25 degrees Celsius ice. It's very fast. It will happen very fast in short span of time. But the same 25 degree change, if you are trying to do with water, right, it will take a lot of time. Maybe like 2x of what is happening for ice. This is very, very important. And if somebody asks you what is the reason behind it, you need to intellectually tell that it is because of specific heat of ice close to half that of what is the specific heat of water.